started it. So
okay, no problem.
Just
yeah, Munna, do you mind? Yeah.
no. Tanga will sir will.
Okay.
Yeah. Okay. Yeah. Happy to have another APRG seminar, and actually there are two seminars today, and then first seminar is going to be given by José María Martell from ICMAT Madrid, and welcome to the APRG seminar, and he's going to talk about elliptic operators in rough domains. Okay.
Okay, thank you. Thank you very much. It's a great pleasure to give this talk. Is even you see nowadays with this kind of technology is easy to give a talk in India without needing to travel, but of course I would like at some point to visit you. So what I'm gonna discuss today is I'm gonna mostly survey some of the results that I have been working on this field of elliptic operators in rough domains. But in particular, I will be focusing the very last part about some recent result that we have obtained with my PhD student Pablo Hidalgo Palencia and my postdoc Min Cao. So the topic is elliptic operators in rough domains. I'm gonna start with some overview of what is known in this field. Okay, so let's start. So I'm gonna get back to 1977, where Dalbert proved the following fundamental result in the area, which says that you are working in Rn+1 and you consider a Elliptic domain. So he showed that the harmonic measure is a weight in the Reverse Hölder 2 condition with respect to surface measure. So here I'm going to explain in a moment what is harmonic measure, but you may omega is what is called the harmonic measure. Sigma is here the surface measure on the boundary. And these Reverse Hölder 2 conditions, for those that are familiar with weights, are going to be easy to recognize. So I'm going to denote a small k for the Radon-Nikodym derivative of omega with respect to sigma. So omega being in Reverse Hölder 2 means that omega is absolutely continuous with respect to surface measure, which is sigma, and it satisfies this L2 estimate, right? So what they say is that the Radon-Nikodym derivative is in L2 in this scale invariant fashion. So why this condition about harmonic measure is important? Because this Reverse Hölder 2 condition amounts to be equivalent to the solvability on L2 for the associated Dirichlet problem, right? So I'm going to use this calligraphic L for the Laplacian because I'm going to use delta for something else. So what you are trying to show is the harmonic extension in a domain of the function f, right? So you prescribe u on the boundary equal to f, which is a function in L2 with respect to sigma, and you find what are the harmonic solutions on the domain whose boundary trace agrees with f. And you see the way this solvability is understood is in the sense that because your function is in L2, you expect this non-tangential maximal function. The non-tangential maximal function is the maximal over some kind of cons that you can, classical cons that you can construct in the Elliptic domain, right? So as you can think here, this is an L2 Dirichlet problem, and this Reverse Hölder 2 condition is equivalent to the L2 solvability. So what is the heuristic of this thing, right? So the harmonic measure allows you to write solutions using this integral representation, right? So harmonic solutions can be written as this integral again with respect to this harmonic measure of the function f. So now you can understand that if your function is in L2 and this is absolutely continuous with respect to sigma, this is in L2 of sigma. So basically you have to think that f has to be in L2 with respect to sigma in order to use Hölder inequality. So this is the heuristic behind that. So typically Reverse Hölder 2 amounts to L2 solvability because this duality between L2 sigma and L2 sigma. Okay. So this is a fundamental result in the area, and this is regarding Elliptic domains. So it's a natural question whether you can go beyond Elliptic domains. You can consider something which kind of generalizes Elliptic domains. And in that case, maybe you don't expect to have maybe Reverse Hölder 2. Maybe you expect to have some maybe weaker condition, right? So this condition is weaker as 2 gets close to 1. So maybe rather than considering L2 integrability of the Radon-Nikodym derivative, or what is called the Poisson kernel, maybe you consider that k is going to be in L1 plus epsilon. So in particular, what you are thinking this is in this domain, maybe you expect to have omega in A infinity, looking at the infinity as the union of the Reverse Hölder P classes.
Just can you go little? Can you slow your pace a little bit slow? Slow your pace a little bit, please.
Yeah. Okay. So so what I'm saying here is that in these more general domains, maybe you don't expect to have L2 integrability. Rather, you expect to have maybe some kind of LP integrability with P close to 1. So in particular, this will be equivalent to the membership of harmonic measure to the class A infinity, right? And in terms of solvability, this will imply that you have solvability for some value Q, right? For instance, if you have your harmonic measure in reverse Hölder P, you expect solvability in LP prime. Because again, this duality again writes in your functions, if this is in LP, so this has to be in LP prime. So being in A infinity is equivalent to having solvabilities for some finite Q. So that's somehow the idea, trying to go beyond Lipschitz domains. Okay, so let me, because I have mentioned already what is the harmonic measure, what is the solvability. So let me consider and let me try to give what is the setting on which which will be working, right? So we are going to consider omega. We are working in Rn plus 1, right? And n is greater than 2. So this means that ambient space is at least dimension 3. Some of the things can be done in dimension 2, but dimension 2 for the Laplacian is a little bit different because the fundamental solution has a logarithmic growth, and then this kind of is a little problematic. So in order to be safe, I'm going to consider ambient space dimension at least 3, right? And and I don't want to use the word domain because sometimes when you use domain, you understand some connectivity. We're going to discuss connectivity in a moment. So for the moment, omega is an open set, right? So what is this harmonic measure? So the harmonic measure is not really a measure. It's actually a family of probabilities on the boundary. So which comes from an abstract point of view when you try to solve the classical Dirichlet problem. So here you can see the classical Dirichlet problem. Remember that calligraphic L is the Laplacian. So you look for harmonic functions in the domain in omega so that U restricted to the boundary is equal in some way that maybe you have to understand some function which is continuous with compact support. The set omega doesn't have to be bounded, so it could be that it's unbounded. So that is why you have to consider continuous with compact support, right? So there is an abstract way using maximum principle to solve this problem in general, and by Riesz representation theorem, this is telling you that U has to be written against at every point x. U has to be written as the integration of f against this family of probabilities. So the family of probabilities comes from showing that solving this problem is equivalent to having a bounded function, right? So this is where harmonic measure comes from. So this is an abstract object. So for the moment, we don't have any properties. And most of the times, if you want to understand the Dirichlet problem, you need to obtain properties of harmonic measure in order to ensure, for instance, that your Dirichlet problem is solvable in L2, in some L4 or some other condition. Okay? So let's look for the moment at the picture. So suppose you have an interval like that. And then there is a very nice interpretation of what is the harmonic measure. So as I said, the harmonic measure is a probability that can be understood in the following way, right? So you give a set on the boundary, so family probabilities on the boundary, and then you take for any point on the domain, you look at all the Brownian travelers that start from X and escape the domain, right? So the harmonic measure is exactly the probability that this Brownian traveler escapes from the domain through the set F. So this is, although we don't use this much in the theory, this is a good, this gives you a very good intuition, because this is telling you that in order to calculate this probability of a set, you need to have accessibility to the boundary, right? So for instance, from X, we have some kind of accessibility to the boundary, but if you think it's something which is a narrow cusp or something like that, it's very likely that the Brownian traveler is going to be stuck in the border, right? So it's going to be difficult for you to go through something which is very narrow. And this is something that is going to appear in a moment. Okay, so this is this interpretation that tells you that harmonic measure is related to how, if you are able to get to the boundary or not. All right, so I'm going to use the following notation. Delta for me is going to be a surface ball. So what is a surface ball? A surface ball is the intersection of a ball center of the boundary with the boundary, right? So it's this thick line, purple line, right? So this is where I'm going to use a surface ball. And sigma is going to be the surface measure, which is, remember that I'm working in n+1 dimensions. So this is the n-dimensional Hausdorff measure restricted to the boundary. So I'm thinking that my boundary is n-dimensional, right? Something that I'm going to assume all the time is that my boundary is alpha-David regular. So what is alpha-David regularity? Alpha-David regularity is exactly that the surface measure of any ball, any surface ball, is comparable to R to the n. And this is true for every x in the boundary and for every radius, right? So this is a scale invariant condition, and you have to understand that the constant is the same for all radius and for all positions. So this is a scale invariant condition, right? So no matter how big is your ball or how small is your ball, your surface measure is like R to the n. So what is this condition? You may think that this is a quantitative version of being n-dimensional, right? So in a sense, what you are showing is that boundary is essentially like R to the n in terms of measure. It doesn't have to be in terms of regularity. Okay, so delta is going to be the surface ball. My measure is going to be like R to the n-dimensional measure. Okay, so let's talk about something that was introduced by Carleson and Kenig, this NTA, non-tangential accessible domains, or something which is also called core R domains. Okay, so we know that the domain is open, right? So because it is open, given a ball, you see here in blue, you can always find another ball in the domain, but you have no control if your ball is big or small, or you have no control whether the ball is away from the boundary or not. So what is the Corkscrew condition? The Corkscrew condition is a scale invariant condition that guarantees that given any of these balls, there is a ball with a appropriate measure, right? So the Corkscrew condition says that for any ball centered on the boundary, you can find another ball in red so that this ball has essentially the same time. There is a constant small c here that is the same everywhere. So again, this is a scale invariant. That means that I can move my ball all around the domain, and I can zoom in, zoom out with different R, and I always have the same constant. So I can always insert a ball in the domain. Or in other words, this is the same as saying that the measure of the part of the ball that is inside the domain is comparable to the measure of the ball. Right, so Corkscrew condition is equivalent to a quantitative open condition, right? See, this is a quantitative version of the topology of the topological property of being open. And you can do the same thing using connectivity, right? So because if you assume that your domain is connected or is path connected, you know that there is, given 2 points, there is a path that joins the 2 points. But you don't know in principle, unless you assume something else, whether this path is going to be very long, right? So it could be that maybe to join this point, maybe I could just, in this case, I could have just taken a straight line, right? So, but maybe you start kind of getting very close to the cusp or something like that, maybe you have to be away. And the important thing in these elliptic operators in the Laplacian is that it's convenient to have your path away from the boundary because of what is called the harmonic inequality, right? So you can quantify, you can make this connectivity quantifiable, right? And you can quantify that in the following sense. And this is what is called the Hartmann-Chain condition. What you assume with the Hartmann-Chain condition is that given 2 points, there is a chain of balls in this fashion, so that this allows you to join these 2 points using this spline or using this polygon, right? And at any point, the radius of any ball is comparable to the distance to the boundary. So this means that you see, for instance, you see that is typically this is what a Hartmann-Chain condition does. As you go away from the boundary, the ball gets bigger. And then there is a control in the number of balls in terms of what was the original distance to the boundary and what is the distance between the 2 points. So notice that, for instance, if I start with something which is very close to the boundary, because my initial ball has to be comparable to the distance to the boundary, I have to start with something which is very small. And if I get away from the boundary, my balls are allowed to be bigger. Okay? So this is the way to understand this. There is a quantitative version of openness, which is the Corkscrew condition, a quantitative version of connectivity, which is the Hartmann-Chain condition. So let me present a couple of examples on which these conditions are not satisfied. So for instance, you see this condition here where there is no Corkscrew. There is no Corkscrew because there is so narrow path that you cannot insert a ball inside here. This is easy to see, right? And why I don't have a Hartmann-Chain condition in this picture here on the right? because you see that the distance between the 2 points and the distance to the boundary are comparable, but you need more and more balls as you approach the boundary, right? Because remember that you start with balls that are very tiny as you approach the boundary. So when you have to go around this kind of lamp, and then if you start with points that are getting closer to the boundary, get very close to the boundary, then you need more balls and balls. So the Hartmann condition, remember that I haven't written the condition because it's quite technical, but this is imposing that the number of balls is controlled by the distance of the 2 points and the minimum of the distances to the boundary. So as you approach these points to the boundaries, this condition, this ratio is always 1 by the number of balls is bigger, right? So this is just something for you to give the intuition. And then let me then introduce what Jerison and Kenig introduced in 82. What is a Corral domain? A Corral domain is a domain that satisfies an interior corkscrew and Hartmann condition. This means openness and connectivity in a quantitative way, and an exterior corkscrew condition. This means that you also assume that this corkscrew condition on the exterior of the domain. And you assume also ADR, right? You use the word NTA, non-tangential accessible, if you remove the ADR condition. But I'm going to use ADR all the time, so I'm not going to introduce that. And let me also introduce another notion, which is a one-sided Corral domain, on which I remove the exterior corkscrew. Because you see, in a sense, I want to remind you that you are solving the Dirichlet problem. So the question is, why do you need to introduce a condition on the exterior if you want to solve something in the interior of the domain? And this is going to be clear in a moment, right? So one-sided Corral is interior openness and connectivity, and exterior openness in a quantitative way. One-sided Corral domain, you remove the exterior corkscrew. You may think that, oh, this is very nice, you just remove the exterior corkscrew, things are more or less the same. So there is I will see in a moment that this is deep sense of the geometry and regularity of the pattern. Okay, so this is the extension of the result that I put before for Lipschitz domains. So this is a result proved by David and Jerison in the 90s and independently by Sems in the late 80s, right? So in the case that you have a Corral domain, then your harmonic measure is in A infinity. A infinity, remember, is the union of the reverse Hölder P classes, and A infinity with respect to surface measure imposes that this is absolutely continuous with respect to sigma, and you have this LP integrability, right? So this is a self-improvement of the integrability, right? So as I mentioned before, because I can write all solutions using this integral representation, if my harmonic measure is in LP locally, which is that the reverse Hölder P says, this is pairing with a function which is LP prime. So reverse Hölder P condition is equivalent to LP prime solvability in the very same way, in the sense that this non-tangential maximal operator is a boundary operator in LP prime, right? So this allows you to solve this harmonic extension problem with data in LP prime. For some finite, because A infinity amounts to be some reverse Hölder P, this amounts to solve this problem for some finite P prime. Okay. All right. So let me get back to this discussion. So this result that you see here is for Corral domains, and I introduced the one-sided Corral domains. So what is really why this condition, or why these authors use the exterior corkscrew condition? And the exterior corkscrew condition is very important in terms of the regularity of the boundary, because what this says is that when you have, without any connectivity, if you have a domain with interior and exterior corkscrews, the boundary is uniformly rectifiable. And I'm going to explain what is uniformly rectifiable in a moment. But in a sense, it's like Lipschitz. It's more general than Lipschitz, but it's a generalization of Lipschitz. So only the fact that you have corkscrews, but you have this kind of two balls of similar size in the interior and the exterior, forces the boundary to be flat in a sense. This was proved by David and Jerry. So what is this uniformly rectifiable thing, and what is this important? Uniform rectifiability has many different characterizations, but one thing that has to be with the smoothness over the regularity of the boundary is what is called big pieces of Lipschitz images. So what is this? So you say that this is uniform rectifiability is of the boundary, but you can write for a set. So just think that E is the boundary of your set, So you take a closed set, which is the boundary, and you take ADR. So what big pieces of Lipschitz images says is that for any scale that you put on the boundary, your domain or your boundary agrees with the image of a Lipschitz graph. Okay, so this is what this says. This says that maybe you have a ball, and maybe you don't know that the whole ball, you take a ball, you take a surface ball, and you don't see a Lipschitz graph in the whole boundary, but you know that there is a portion which is fixed that agrees with the Lipschitz image, right? So this says that, for instance, there is a 1% of every ball on which your boundary agrees with the graph of a Lipschitz function. And the point is that this 1% is maybe 1%, or maybe it's 1 over a million, but it's always 1 over a million for every ball, no matter where is the center of the ball, no matter what is the radius. Okay, so this is the idea. It's a generalization on Lipschitz, right? In a Lipschitz domain, every ball, in every surface ball, you see a Lipschitz graph. Here, what you say is that I don't see a Lipschitz graph all over the ball, but I see it in some fixed portion. The portion can be very tiny, but still there is a fixed portion. So this is from the point of view of geometry, but from the point of view of harmonic analysis, there is another characterization which is very important, that a set or a boundary of a domain is uniformly rectifiable if you have, besides having alphas of irregularity, all nice singular integral operators are bounded in the domain, right? So what I'm saying is that in a set, uniformly rectifiable sets are the domains on which you can extend the Calderon-Simon theory in a good way. What is a nice singular integral operator? Operator with a nice smooth odd kernel, right? So you take one of these convolution type, they say the Riesz transform, right? So you take the Riesz transform in Rn plus 1, right? In Rn, and then you put it in your domain, and then you think, oh, what is this operator bounded in L2? This is only happens if the domain is fully rectifiable, right? So these are here the 2 points of view. One, the point of view of flatness or regularity of the boundary in terms of at least there is a piece which is Lipschitz, or in terms of singular integral operators, this is a setting on which you have singular integral operators which are bounded on L2. In a sense, if you remember the theory of spaces of homogeneous type, the theory of spaces of homogeneous type says that whenever you have a Calderon-Simon operator which is bounded on L2, you can show that the operator is bounded on LP, right? So this uniformly rectifiable takes care of the L2 part. When you have L2, the operators are bounded on L2, you can use the space of homogeneous type theory, and so that all these nice singular integral operators are bounded in LP, because you have a doubling. ADR is even stronger than that. Okay, so you don't have to remember the uniform rectifiability thing. The only thing you need to remember is that uniform rectifiability is something about flatness or regularity of the boundary. Okay, so as you see here, the difference between choral domains and one-sided choral domain is that the boundary is regular. So dropping the exterior corkscrew allows you to introduce sets which are fully non-regular. And this is, for instance, you may introduce something which is called the four-corner Cantor set, which is very scattered and is very irregular. Okay, but still the question is why in this result that I put before, I need to have this kind of regularity of the choral domain. You may think, oh, maybe there is a way to generalize it. The answer is that no, you cannot generalize. And I wanna remind you what are the two conditions, and let me obtain the following, or let me present the first result of this talk. Okay, so suppose that you have one-sided choral domain. So you have alpha-David regularity of the boundary, and I have connectivity and openness in the interior only, and when I don't have fixed exterior. So what this result says is that exterior corkscrew is equivalent. The harmonic measure to be in infinity. Remember, this is equivalent to solvability, and it's equivalent to uniform rectifiability. So in a sense, what this is saying is that you cannot, assuming interior and Harnack chain, assuming connectivity and openness in a quantitative way, you cannot drop the exterior corkscrew and try to solve the Dirichlet problem with data in some LP, because solvability of the Dirichlet problem, which is the condition 2, is equivalent to obtain either exterior corkscrews or uniform rectifiability. Okay, so this is the first main result. So 1 implies 2, that corner domain implies uniform rectifiability, is the result that I put before. Sorry, 1 implies 2, that corner domain implies infinity, is the result that I put before, David and Jerison or SEMS. 2 implies 3 is a result that we obtained together with Stig-Hoffmann and Uriarte in 2014. So what we obtained was to show that when you have an infinity, this automatically forces the boundary to be regular. This is a free boundary result. Good properties of solutions implies uniform rectifiability, which is regularity of the boundary. And then 3 implies 1, which is uniform rectifiability, implies exterior corkscrew, is a joint result together with a Sam, Hoffman, Nystrom, and Thor. So what we saw here is that flatness or regularity of the boundary implies also the exterior corkscrew. Remember that I mentioned before that in a corner domain, the 1 implies 3 was known. So it was left in this problem to show that flatness of the boundary implies that actually you have exterior corkscrew. So assuming interior corkscrews are not same, regularity of the boundary tells you that the exterior is T. This is the way to understand. Okay, this is so far for the Laplacian. So my first question is, can we go beyond the Laplacian? Second question, can we do perturbation? So suppose that we know this for the Laplacian. Is there any operator that is close in some sense that are going to allow me to obtain the same property? And then the next property is that can we relate A infinity to some property of solutions? Because for the moment, I know that A infinity is equivalent to solvability, but I want to say, okay, maybe I have a family of solutions. I want to see this relates to having some property of the solution. So we go to this in a moment. Okay. So first of all, let's generalize the operators. So this is the class of operators that I'm going to be considering. A divergence form elliptic operator is minus divergence of A gradient U, and A is a metric which is depends on X. It's going to be real, and it's going to have this is what is called elliptic, right? So you have this accretivity, and you have that the coefficients are bounded. The case that I put before the Laplacian is what you put here, the identity. The identity is constant, so of course it satisfies this, right? So this is what is called an elliptic operator. So this is the accretivity, and this is saying that all coefficients in the operator are bounded. Are in L infinity, doesn't have to have any smoothness or any regularity. Okay. So in the very same way that I introduced before the harmonic measure, I can introduce an elliptic measure that allows me to construct solutions for the classical Dirichlet problem, right? So this is the class of elliptic operator. Okay. So what are the classes of operators that allow you to go beyond the Laplacian, right? So this is what is called the Kenig-Pipher operators. So these are operators with variable coefficients. So now you assume some kind of regularity, locally Elliptic, and then you assume the following two things. You assume that if you take gradient of A, delta is the distance to the boundary. It's the function that taking any point in the domain, measure the distance to the boundary. This is bounded. So this means that you have some control of the oscillation of the A near the boundary. And then the second condition is that if you take gradient of A squared delta, is a Carleson measure. This is just this is saying that this is a Carleson measure, is something that measures things in the domain, but behaves like an n-dimensional measure on the boundary, right? So this is the classical definition of a Carleson measure, right? So these are the Kenig-Pipher operators. So these are very important, and these are the natural classes.
So what is delta here?
Delta, remember, delta, small delta is the distance to the boundary.
Oh, yeah.
Measures for any point S, the distance to the boundary. And this delta here, capital delta, is the surface bond, right? So this result says that what we obtained before for the Laplacian can be extended to Kenig-Pipher operator. Given the very same setting, if you have a Kenig-Pipher operator, core of the domain is equivalent to A infinity. And again, this is equivalent to having uniform flatness of the boundary, uniform rectifiability. 1 implies 2 what was obtained by Kenig-Pipher in 2001, and 2 implies 1 is a result together with Stig-Hoffmann, Svetlana Maiboroda, Tatiana Toro, and Siguisa back in 2021. Okay, so this is telling you that this is, in a sense, this is the natural extension of the Laplacian. So this is a class of operators for which you recover the result for the Laplacian. Okay, so remember there were several questions. One, can we go beyond the Laplacian? This is one result. The next result is, can we do perturbation, right? So this is the perturbation. So now you have two operators. And the idea, you have a nice property for L naught, and you want to see what are the operators L that can be seen as a perturbation of L naught. And this is there was a notion of perturbation introduced by Fefferman-Kenig-Pipher, and the perturbation is the following. So you take the discrepancy of the matrices in within regions, right? Symbols that are away from the boundary. Remember, delta to the x is distance to the boundary. So if I take the ball center of x distance delta to the x to the boundary, you are away from the boundary. This is a windy region, essentially, right? So this is, if this is a Carleson measure, this is what we call a Fefferman-Kenig-Pipher perturbation, right? So what this result says is in the very same setting, assuming interior cos-cruz and interior connectivity, then one is in A infinity if and only if this is in A infinity. Or in other words, for instance, if we know that the Laplacian is in A infinity, then we know for any perturbation of the Laplacian. The perturbation doesn't have to be a small perturbation. Carleson measure means that this is finite, right? If you want to think about the small perturbations, what you are able to obtain is that you preserve the same exponent. Remember that the infinity is a reverse Hölder P class. So you assume here Carleson measure with very tiny norm, then you can preserve the P in the reverse Hölder condition for one and infer to the other one. Okay, so that's it. Okay, so this was proved in 91 for Lipschitz domain and extended to choral domains by Fefferman-Kenig-Pipher, and extended to choral domains by Milakis-Pipher-Toro. So our contribution was to say, okay, perturbation doesn't require to have exterior cos-cruz. We have the very same theory, you can do the same thing. Okay, so this is perturbation. All right, and then the other question that I put before is I was talking about what operators are more general than the Laplacian. That was the Kenig-Pipher operators. What can you do with perturbation? And the other property that I mentioned before was, is there any other property that kind of encodes this A infinity property? And this is what is called Carleson measure estimates. So let me introduce the following notion. I'm going to use LCME. CME is Carleson measure estimate, and this is Carleson measure estimate for all bounded L solution. This is something that is very classical, is whether anytime you have a solution which is bounded, in the case of the Laplacian, suppose that you have a harmonic bounded solution, whether gradient of U square distance to the boundary is a Carleson measure, right? So we say that one operator has Carleson measure estimates for all bounded solutions, is for any bounded solution, then you have this Carleson measure condition, right? So this is a condition that must be true for all bounded solutions, right? So we have the following characterization that says in the very same setting with connectivity, for the time everything is with connectivity, A infinity is equivalent to having this property, right? So in a sense, A infinity, remember that is constructed solutions for data in LP for some finite P, and Carleson measure estimates is constructed solutions that are bounded, right? So this is a condition for solutions in LP, and this is a condition, Carleson measure estimates, a condition for bounded solutions, right? So this is a very good proxy. Rather than working with solutions that may have a singularity, because in LP you can have a singularity, it suffices to work with L infinity solutions. If all L infinity solutions satisfy a Carleson measure estimate, you have the very same condition, right? So this extends previous results that was proved in choral domains by Hidalgo, Carleson, and Kenig, and also by Kenig-Pipher-Toro for Lipschitz domains, right? So we prove it in general. Okay. So let me summarize what we have obtained so far, because now I'm going to go beyond this setting. We have a one-sided choral domain. In the one-sided choral domain, I want you to retain that the main property is strong connectivity. So Harnatz's condition, this quantitative connectivity must be seen as a strong connectivity. For a strong connectivity, we have the following properties. First of all, for a general L, we know that A infinity is the same as Carleson measure estimates, right? So this is a property of solutions. We have a class of operators that are beyond the Laplacian or the contained the Laplacian, for which we know that A infinity is the same as having some geometry or regularity. Remember that choral domain is something about something on the exterior, which you can see as geometry, but UR is about regularity at the boundary, right? So A infinity condition is equivalent to obtain both geometry and regularity. And then we also have perturbation, right? You can see perturbations perturbation in terms of perturbing the infinity condition, or because I know already by the first item that I infinity is equivalent to Carleson measure estimates, I can write perturbation in terms of Carleson measure estimates. If I have Carleson measure estimates for solution for L naught, so I have for solution of L. So in a sense, what I'm saying is that these conditions are stable under perturbation, right? So for a Fefferman-Kenig perturbation, I can A infinity is stable, or Carleson measure estimate is stable, right? So this is so far what I have obtained. And the main ingredient is a strong connectivity. My next question is, what can you do if you don't have a strong connectivity, right? Can you go beyond strong? Can we prove something without a strong connectivity? And this is what I'm gonna dedicate the next part of the talk. Okay, so the question is, what happened with the non-connected case? Maybe the domain is connected in a qualitative way, but we are not gonna impose any quantitative condition. So we start with very bad news. Even if the case of the Laplacian, this is not true. You have a domain, Bishop and Jones constructed a domain for which the boundary is UR, but the harmonic measure is not even weak A infinity. Why do I use weak? Because in the domains that I mentioned before, harmonic measure was doubling. When the harmonic measure is not doubling, then rather than working with A infinity, you have something which is called weak A infinity. It's a weak reverse Hölder condition, but that's not important, right? So this is already failing. So you look at the second property here. In the case of the Laplacian, I know that A infinity is equivalent to uniformly rectifiability. Without a strong connectivity or without UR, then you already have a problem. So this means that there is something about connectivity that is important. Remember, before with a strong connectivity, I'm able to show that these conditions are important. But here we have regularity of the boundary, but still we don't have A infinity. So something is going on, right? Okay. So, but remember, I go back to this thing. I know that maybe for A, I have A infinity. I know that with nice property, I have Carleson measure estimates, but maybe A infinity is not true, but it could be that Carleson measure estimate is true. But remember, in this case, they are the same, but maybe they are no longer the same, right? And this is what happened with that connectivity. If you have a domain, just interior cross group, doesn't have to be even connected at all. The boundary is gonna be ADR all the time. Uniform rectifiability of the boundary is equivalent to Carleson measure estimates for the Laplacian for the moment. Okay, so in the case of the Laplacian, uniform regularity of the boundary amounts to these Carleson measure estimates. Remember that is having properties for bounded solution, right? Okay, this was the implication 1 implies 2 is a joint paper with Hoffman and Mayboroda, and the implication 2 implies 1 was proved by Garnett, Morgu, and Tolsa. Okay. So we know that without connectivity, we still have that UR is equivalent to Carleson measure estimates. But remember, by the Bishop-Jones example that I put before, this means that Carleson measure estimate is not equivalent to weak A infinity, not even weak A infinity. So now we are talking about very different problems. What we are losing here is connectivity. Without connectivity, regularity of the boundary is no longer connected to A infinity, which is solvability of the Dirichlet problem with singularity. Okay, so what is the ingredient that is missing? So I know with a strong connectivity, which is Hartmann-Chain condition, I can prove that these two things are equivalent. Okay, so this was a major result, a breakthrough in the field. Was this result proved by Hassan, Hoffman, myself, Morogoro, and Tolsa, on which we obtained a characterization of weak A infinity in the following way. So harmonic measure is in weak A infinity if and only if we have uniform rectifiability plus some connectivity, which is weak connectivity, which is weak local joint. I'm not going to define this because this is very technical, but I'm going to get back to what I mentioned before. So remember, I'm going to get back to this slide. Sorry, this one. Okay. So remember that, hold on a second, is it one? So remember what I mentioned before with this picture. I say that harmonic measure is related to how do you get to the boundary. What is this weak accessibility or weak connectivity? So with this connectivity, it says that maybe you can access for a ball a part of the boundary, but maybe not all the boundary, right? So this weak connectivity says that rather than accessing to the whole boundary, maybe in every ball you access to maybe half of the ball, or maybe to 1/1,000,000 of the ball. So it's more or less the same thing that I mentioned before with big pieces. So you have a piece which has some fixed ratio, so maybe 1% of the ball or 1/1,000,000 of the ball, on which you have accessibility using this kind of Brownian trappers. So this is somehow the idea. I don't want to get technical because it's very, very technical, but weak connectivity is getting accessibility in a non-tangential, maybe like in a conical region, to some portions of the boundary, right? So this was the condition that was missing. Before I use strong connectivity, this is much weaker. This is much weaker, but I still allow you to be weak infinity. And this is an honest weak infinity because the harmonic measure is not doubling. And having the harmonic measure not doubling gives you many, many problems. Okay? Okay. So getting back to what we know. Once in the corner domain with a strong connectivity, we know that everything is equivalent. With no connectivity, we still keep the Carleson measure estimate equivalent to uniformly rectifiability, but we lose the weak infinity. And then you see, we know, on the other hand, this kind of weak local connectivity is not going to appear anymore. Okay. So, but my next question is the following. Okay. So I know that these two things are equivalent here for strong connectivity, but I lose this weak infinity property. Is there any something which is weaker than the weak infinity property that allows me to complete this equivalence? Weak infinity is too strong because you need connectivity. So if you don't have connectivity, this weak local job, weak connectivity, is there any possibility to obtain something in terms of omega L? It must be weaker than weak infinity, right? So this is the first question. Can we go beyond weak infinity and still get a characterization here? Second question, is there a perturbation theory? Suppose that we have Carleson measure estimates for L naught. Can we get Carleson measure estimates for L? Or if we have this property yet to be defined for omega, can we solve the same property for omega? Okay, so this is what we're going to do. And we're going to do using what is called a corona decomposition. Okay, so what is a corona decomposition? A corona decomposition is, first of all, we are working with alpha-David regularity boundary, which is doubling. So this means on the boundary, we have a dyadic grid. This is just a collection of what we call cubes. They don't have to be cubes, but they have the very same properties of the classical dyadic cubes. They have children, they have parents. Every children has a parent, and the very same property. They are organizing generation, right? So what is a corona decomposition? A corona decomposition is a way to organize dyadic cubes in the following manner, right? So we split cubes in good or bad, right? And we're going to call G for the good cubes and bad for the bad cubes. So I have three things, bad cubes, good cubes, and F is a new thing. So good cubes have been organized in what is called trees, and these trees are semi-coherent. Semi-coherent trees are stopping time trees. So this is a stopping time condition. So probably you're most familiar with that. What does it mean semi-coherent? Semi-coherent means that for any tree, there is only a top, right? So you have your tree and you go using the inclusion to just one top. And then semi-coherent means that if you have a cube that is in the tree, any cube that is between a cube in the tree and the top is in the tree. So this means that once you are in a tree, you can go in between and you are remain a tree. So this is a connected tree, right? So this is semi-coherent. And you think of a stopping time argument, for instance, for the Hardy-Blum maximal function, the stopping time argument, this is semi-coherent, right? Because you stop when you stop, you think on a stopping time condition, you stop whenever something happens. So this is a semi-coherent typically by definition, right? So a corona decomposition is a split in an organization of cubes in good and bad. The good are split into semi-coherent or stopping time regimes, and then you want to prevent not to have too many cubes, not too many trees. So what you assume is that these bad cubes and the top of the tree satisfies a Carleson packing condition. The Carleson packing condition is written here. If something satisfies a Carleson packing condition, this is telling you that this doesn't happen not very often, right? So this means that there are not many bad cubes. You can have a lot, but there are not many in some quantifiable way, and you don't have that many top trees. So this means that there are just a few, in a sense, there are just a few bad cubes, and there are not that many stopping time arguments, right? So you have the number of trees in this good subdivision is not very large. Okay, this is the way to understand. Okay. So let me then introduce the condition that is beyond weak infinity. So I'm gonna say that omega is equivalent to sigma if in the corona sense, if I have the following condition. I have a corona decomposition so that the average of omega over sigma is comparable to 1, depending on t, right? So for any of these trees, in the good trees, remember the bad cubes is something that the bad cubes all the time, there is nothing that you can do. So you can only work with the good cubes and the trees, but the trees are most of the action, right? So what this is saying is that something is omega is comparable to sigma if you know that omega over sigma is comparable to 1 for every cube, right? I'm going to assume the following thing. This is the green function. So all these operators have an associated green function, right? I'm not going to introduce it. So we know that this is comparable to sigma in the corona sense if I have more or less the same thing. The sub over given a cube, you always have like a ball that contains the cube, right? And then you look at the points that are in the ball containing the cube that are away from the boundary. And then you tell that the supremum of this is comparable to 1. This is kind of technical. So just think that G is comparable to delta. The Green's function is comparable to the distance to the boundary. Okay? And this is true in the corona decomposition, in any tree. Right? If you want to be precise, what is this one? One is exactly what happened at the top of the tree. Basically, QT is the top of the tree, if you want to think about that. Okay? So the corona decomposition. And then let me introduce what is called partial Carleson measure estimate. Partial Carleson measure estimate says that you are going to have a Carleson measure estimate, but not in the whole ball. What you say is that for every cube, there exists a point which is the distance to the boundary is comparable to the boundary. I cannot draw, so it's typically this is kind of easy if I draw a ball. So this is a corkscrew point in a sense, right? So what this is that there exists a corkscrew point for which I have this Carleson measure estimate when I look over these balls centered at the corkscrew point. Look at, I put here 0.9 distance to the boundary. So this is a ball which is fully contained on the boundary. So remember, Carleson measure estimate tell you that you have to fill the whole ball. Here I'm just taking small balls that go all the way to the boundary, but you don't fill the whole thing, right? And this is for all L infinity solutions. So what this is the result that we obtain with Min Cao and Pablo Hidalgo Palencia is the following. Assume interior corkscrew and alpha of irregularity. The following are equivalent. Omega is comparable to sigma in the corona sense. G is comparable to delta in the corona sense. We have partial Carleson measure estimate, right? So this is what we obtain. So in a sense, what we obtain is that we have a proxy for the infinity solution. I will explain why, which is equivalent to this nice property for the Green's function, which is equivalent to this more kind of weaker version of the Carleson measure estimate. Okay, I have an overview of one of the proofs, but I'm going to skip it. So basically, 1 implies 2 is what is called Carleson-Pfeffer-Liljefield modulus alpha estimate, which is so that is comparable to delta. 2 implies 3 is an integration by parts argument, and 3 implies 1 is an extension of a previous result. Okay, I had the proof here, but I think I'm running out of time, so I'm gonna forget. I just want to mention the following. Okay, so let me just go over the proof. This is the proof of what we are doing. Is remember that if I have G comparable to delta, I can replace in this inequality G by delta. And what is the difference between in this integral having delta and G? That delta is not a solution, but G is a solution. So once G is a solution, you can do some algebra to write something like that. And now you use divergence theorem to get this integral, use interior estimates, go to G over delta. Again, you use that G is comparable to delta to get back to 1, and then this is that. So this is basically the proof. The proof is kind of easy when you have all the ingredients. The main ingredient is to replace delta by G. And the difficulty here is that in general, when you have connectivity, you can replace delta by G all the time. Here, you can only replace in this kind of component, which are these places where G is comparable to delta. But this is just too technical, so let me forget about that. Okay? All right. So this was our result. Getting again, question, what is perturbation? can we do something for the Laplacian on Kenig-Pipher operator or uniform rectifiability? Is this still equivalent to uniform rectifiability? Is this related to weak infinity? What happens if you have a strong connectivity? Are you able to recover the previous result with a strong connectivity? So these are the questions that I want to address in the following 3-4 minutes. Okay. This is the perturbation result that I put before. If you have a Fefferman-Kenig-Pipher perturbation, it's the same thing that I put before. All these things are stable, right? This is comparable to this for L naught, the same is for L. G is comparable to delta for L naught, G is comparable for delta to Del. Is partial Carleson measure estimate is the same for L naught and for L? Yes, they are the same. Okay, so these properties are stable under perturbation. So this was the first question. Second question, what happens with the Laplacian? Remember that in the case of the Laplacian or in the case of Kenig-Pipher operator, I'm typically able to obtain better results. So this is good news because what I say is that in the case of the Laplacian, all these things are equivalent to full Carleson measure estimates. So this partial, which is way weaker, is equivalent to full Carleson measure estimates, and the boundary is uniformly rectifiable. So this means that my property, even if it looks very weak, still captures the uniform rectifiability of the boundary. Okay? And this is how the result was proved. And there is a very interesting point is that partial Carleson measure estimate was only kind of looking at balls that are moving all the way to the boundary, allows you to get all the way Carleson measure estimates, right? So this is telling you in the case of the Laplacian, you can recover part of the theory. We have the same for Carleson Kenig-Pipher operators. It's a stronger condition, but I don't want to get into that because I want to finish in time. Okay. And how weak infinity and corona compare, right? So you always have this condition. Weak infinity is stronger than corona. They cannot be equivalent because we have the Bishop-Jobs example. In the Bishop-Jobs example, we have corona, we have Carleson measure estimate, but we know that this is true. But we know that they are equivalent when you assume a strong connectivity. So in a sense, what we are saying is that this corona substitutes a infinity when you have no connectivity at all. Okay? Hence, you have this condition, right? Once you know that they are assuming a strong connectivity, then you have that everything is equivalent to what you already knew in the past. Okay? So this is telling you that this condition, that this corona that was looking at the beginning very weak, at the end of the day, is allowing you to obtain that this is equivalent to A infinity under a strong connectivity. So we recover the whole theory by using this corona decomposition, when in principle looks much weaker. Okay, and that's all. I hope you have enjoyed the talk. Thank you very much.
Thank you very much for a very informative talk. Are there some questions?
Yeah, I have one or two simple questions maybe.
Yeah.
So what is the condition on the boundary actually which will ensure this ADR condition?
What condition?
You have asked, and so how do you know that this domain has really ADR condition?
ADR condition. Okay, so well, that is interesting. We have been able to do stuff with connectivity and not assuming alphas of irregularity. If you don't assume alphas of irregularity ADR condition, then you have to assume what is called the, how was it called? Is the, now it's not coming to my mind. It's something about the exterior, which is the capacity density condition. Because, okay, alphas of irregularity is telling you that the boundary is sufficiently thick. So what happens is the boundary is not sufficiently thick, that maybe you need to know that the exterior is sufficiently thick. It's something about capacity, which is much weaker than exterior cross-group, but is connected to having some property which is called Hölder continuity at the boundary. Right? So if you don't assume alpha of irregularity, you can do part of the theory, but now, for instance, everything that is about A infinity, you talk about A infinity with respect to sigma. But in that case, if you don't have ADR condition, then sigma doesn't make any sense, right? So maybe typically you do all the time. Maybe you have some other measure there. So you can do some other things. In general, without connectivity, we are still trying to figure it out what to do. It's not clear at all.
And another thing, actually, you have mentioned in your talk that if somebody is asking,
No.
No.
Go
Okay,
ahead.
so so in your talk you mentioned that all nice pseudo differential operator are bounded, right? Yeah, some equivalence of some condition. So what do you mean by nice? Actually,
You mean in the uniformly rectifiable condition?
Yeah.
Yeah, so
Yes.
if I go back to the uniform rectifiable condition, yes, here. So nice
That
singular
we
operator, just think on the Ruiz transform. The n-dimensional, we are in Rn+1, the n-dimensional Ruiz transform is a odd smooth kernel. So it's a kernel which is infinity away from the boundary, and there is odd. So that's what I mean that nice singular integral operator.
This another small question actually. This corkscrew condition, actually the 2-3 condition, Arnott chain condition and corkscrew condition. You have explained this thing geometrically, but the thing is how quantitative. How can this one means express this thing quantitatively?
Yeah. So okay. So it says, let me go back to this. For instance, let me put this picture, right? So openness just is telling you that there is a ball, which is this kind of big red dot, but you don't know whether the ball is sufficiently big. You don't know whether the ball is very close to the boundary. In elliptic operator, is good to know that you have stuff away from the boundary. What corkscrew condition says is that you have a ball of comparable size. Or if you want to think in terms of measure, what this is telling you is that the measure of the full ball is comparable to the measure inside the domain. Okay, so you think in this example here that it is impossible in here to put a corkscrew, right? Because you don't have a space. So corkscrew is telling you that you don't have these kind of narrow places, right? And the same occurs with connectivity. With connectivity just tells you that you given 2 points, you would know that how to connect, but you don't have control of the length of the you don't have control neither on the length of the path nor if whether the path gets to the boundary, gets close to the boundary or not. With Harmonic chain condition, in a sense, you are optimizing the way you connect points being away from the boundary. So as I said before, is you have to be able to connect this with a chain of balls. So then you have this polygonal line, right? So that the measure of the radius of the ball is comparable to the distance to the boundary. And then the number of ball depends only on the distance between the 2 points divided by the minimum of the distances to the boundary. So in a sense, this allows you to be able to connect using these balls. So why these balls are important here is because that's something that happens for the Laplacian. For instance, if I have a solution in one of the balls, using Harmonic chain condition, I can know that I can compare the solution in one point and the other, only in terms of the number of balls. For harmonic functions, you know this property that U in a ball, the minimum is comparable to the maximum, right? So if you have this chain of balls, now you can start comparing the first ball with the second one, the second with the third one, so forth, so on. So having this Harmonic chain condition, because you are always away from the boundary, you can control and you can compare one solution to the other. So this is telling you that the solution is almost constant in this path. Of course, it depends on the number of balls. So that is why it is important. So here, of course, I have 6 balls. All right. So this is gonna depend. It's gonna start accumulating a constant to the power 6. But still, I have control in the number of balls. So that's the idea. And again, here, if you think on this thing, here I don't have the Harmonic chain condition because as I'm getting these 2 points very close to the boundary, the number of balls are gonna increase. So I lose this control. So in other words, if I have a solution in this point and a solution in this other point, they are not going to be comparable if I get very close to the boundary. So that's the idea.
Are there some more questions?
Yeah, maybe I can ask a few questions.
Yeah.
So you mentioned this Carleson packing condition.
Yes.
And so could you please explain like how is it related to the Carleson measure, or is it also related to the sparseness, like the?
Yes, it's the same. It's the same. In a sense, it's the same. I think the Carleson packing condition is the same as the family. You have to consider what is probably. I think if I remember correctly, it's the same. You think that you see in a sparse, maybe you have something. You maybe have to reinterpret what you mean, but it's more or less the same. It's more or less the same. But you just think of what is for instance, a family just look here at the bad cubes, right? So what is this saying? This is saying you sum overall all the measure of the cubes that are bad and that are containing Q naught. So in order for this to be finite, you better not have like a lot of cubes, because once you have a lot of cubes, you start accumulating measures, right? So basically, what is, for instance, a cone is something that satisfies a Carleson condition. You have a cone on cubes. I mean that you start the chain of cubes that start with a point and go growth all the way up. This is a Carleson condition. So you must understand that the Carleson condition is a kind of a sparseness. And then Carleson bagging condition tells you that, okay, you have from time to time bad cubes, don't get me wrong, but you have a control of the number of bad cubes. So they don't happen that often. So, which is very useful because typically they are bad because you cannot do things in the bad cube. So just think in this property, right? I'm gonna have that omega is comparable to sigma in the tree, but I have no idea whatsoever happens in the bad cubes. But what happens is that the bad cubes are kind of neglectable, right? Because they are just an error and they are small. So that's somehow the idea.
So is it like in some sense the measure, like if I combine the bad cubes, is kind of controllable? Like we can have a nice control on the bad cubes, right?
Yes. This is the case, right? So the bad, you say, okay, I can do things in the good cubes, and in the bad cubes, I do nothing because I have control over them, because there are so little. It's like maybe you say, maybe you have 5 bad cubes, okay, you can do it right. So you just think on this property. If omega is comparable to sigma in all the trees, but maybe instead with 5 bad cubes, that doesn't change the properties, right? Because it's neglectable.
Yes. And one more thing, sir, like for example, like here it seems like you have a doubling kind of condition. So you maybe you can be working with the Christ's construction of the dyadic cubes, right? But there is also a construction by Martell, I guess, and that also works without the doubling condition also, I guess.
Yeah, in a sense, okay, more or less any dyadic grid that you use. I typically use the David-Sims dyadic grid, but maybe you can use the Martell. At the end of the day, what you need to have is organize your boundary in terms of cubes. They have parents, they have children, and some property that you need is that every cube has a ball inside and a ball that contains which are comparable in diameter.
Yes.
So that's the thing you need. And you can also use the Hytonen Kairema cubes, for instance. It's the same. It's the very same thing.
Okay. One more question, maybe like it's a very like when you said like this Fefferman-Kenig-Pipher kind of things. So are you kind of giving a BMO kind of condition on the coefficient matrix, or is it something?
No. Is it just okay? Let me go back to where I introduced the Fefferman-Kenig-Pipher condition. Hold on a second. I just go one more time. Okay, there we are. Right.
Yes.
So this is just a condition about the distance, the difference. There is no regularity of the domains are in the infinity, right? Period. And now what you have is this kind of Carleson measure. Of course, Carleson measure is connected to BMO in a sense, but that doesn't have to be that the coefficients, the gradient of the coefficients are in BMO, because what I guess you mean, right? It's just that the distance.
Sorry. Please go ahead.
No. Go ahead, you.
At some point, I thought that there is also an integral condition, maybe at the later part of the talk, and I maybe got confused with that one. An integral condition, maybe at some point. Why do you define this constant rho as the distance between two metrics?
I know what you mean. Okay, let me find it. All right. No, this rho is this distance to the boundary. It's the same thing. It's the same thing that I put with different letter, right? So you take the discrepancy of the two matrices in a Whitney region, and now this is this discrepancy being a Carleson condition. This is a Carleson condition, right? If this is finite, this is a Carleson condition.
So it is behaving like a lower dimensional measure. It's some.
Yeah. So what you say, because you have an n+1 measure here, the y, but you have divided by sigma, you have a measure. So this is the definition of Carleson. So when you mean finite here is exactly meaning that this discrepancy, when you divide right to the square divided by delta, is a Carleson condition.
Yes. Yeah, now I got it. Yeah, I misunderstand that one. Yeah. Thanks. Thank you very much. Thank you.
Are there some more questions? Yeah, in case there are no questions, let's thank the speaker again. Thank you very much.
Thank you. It was a great pleasure to be to give this talk. Okay. Bye then.
Bye.
Bye bye.